Little music intro there for you. Song is appropriately called Wake Up, so you need to wake up and get ready for the rest of tissues. This is a continuation of the last PowerPoint, so it really, not only the tissues, going through the rest of the tissues, but specifically the extracellular matrix, which I left off with for connective tissues. Again, this is only for the connective category. Nothing else has an extracellular matrix. So extracellular, outside of the cells, but it's still supporting the cells. So the things that are included with the cells in every single connective tissue type, it's going to look different per type, but every single, again, connective tissue type is going to have some relative concentrations of these substances. So specifically, ground substance is water with protein, and it's going to have an adhesive quality to kind of mold things together, to hold the cells together. And then there are also going to be fibers, which there are relative numbers depending on the function of the connective tissue type. There are going to be certain numbers of collagen, elastic, or reticular. Certain combinations of them. Some will only have collagen fibers if it needs to be a lot more dense and taut and withstanding force and torque and friction. And so collagen is something you'll hear about in dermatology, that they'll inject collagen into your face just because it does, like within your skin, you're going to have collagen. And the amount of collagen decreases with age, which is what wrinkles are. Your skin becomes less taut, hence why it starts to sag, and so they can give you collagen injections to give you the appearance of youth. Elastic fibers are going to be more stretchy, and I should have said collagen fibers are a lot thicker. The diameter is a lot larger than elastic. Elastic are stretchy and medium-sized fibers, and then reticular fibers are going to be really fine and delicate, making up some of our organs like the spleen. So we are starting, I would start to number these like I did for bone. Remember, the connective tissue category is by far the most expansive, so it includes not only the most types of tissue, but the most diversity. Epithelial tissue like flat, cuboidal, many of them had similarities, but connective tissue types are going to be fairly diverse. And so first, what we're actually looking for now, I'm going to start showing you things that you can use throughout the year. So the first thing, those little tick marks, what I think, especially for the connective category, I'm really going to try and show you tricks, because these are some that you can get confused. These little black tick marks surrounding this central black space, these are the actual cells. So when it says bone cells, or you might see in your book osteocytes, site means cell, osteo means bone, all of these little black tick marks are going to be the actual bone cells. Everything else is matrix. So those little, again, I think it looks like a sawed-off tree. With the rings surrounding, like within the tree stump. This black space in between is the center of an osteon, so that's actually where the blood vessels and the nerves would go. So that's an open space. And under a microscope, it might look like a larger cell, but it's not. All of those cells are going to rotate in circular patterns around that central, it's called a central Haversian canal. You don't need to know that for this chapter, but again, everything is building into another system this year. There's a lot of collagen in your bones. So bones, the matrix is made up of calcium, salts like phosphorus, and then collagen fibers. Your bones have a lot of collagen. So the two things that you can eat to strengthen your bones, calcium, salts you'll get in foods, but then collagen as well, which I know you don't know what collagen is. You don't just eat collagen, but when you eat protein, we break down the protein from other animal sources into amino acids and then build it back up into collagen. And so obviously bones are used to support the body, that muscles are going to attach to the bones to allow us to move. And they protect us. They protect our internal organs. The rib cage protects our liver and our heart and our lungs and our spleen. The one thing that I would tell you, I think I said, pointed out something on the last PowerPoint, but there is nothing in nature that is as amazing as bones as far as like human anatomy. And it might seem like this inanimate, unimpressive object, but I'm telling you, the reason it's impressive is there is nothing naturally produced in nature, even that we can create synthetically, that is as strong, can withstand thousands of pounds of force, but yet is so light. Think about how cumbersome it would be if we had these really strong things that protected all of our organs, but yet they were really dense and heavy. If you've never felt a bone, we do have real bones in the classroom, and when you pick up a femur, it's extremely light, but that calcium and the phosphate salts and the collagen really aren't dense enough to make them heavy or have a high mass, so that you couldn't play sports and run and jump and move laterally quickly. They really are impressive, pointing to design in my mind, that things don't just like randomly pop up as perfectly made as bones. Yes, we can break them, but that's because of less about force or torque and more about the motion that you came down on the bone in. Maybe it's a spiral fracture, or you like an impacted fracture, which you probably learned from the first activity from my accident. So what I'm saying is that they're just impressive as far as how they work because of the matrix. The matrix is really strong, but yet really light. And bone really should be one of the easiest ones to identify, with the rings on a tree stumps surrounding a dark space. The next one, not as easy. Hyaline cartilage makes up our larynx, which, if you don't know what the larynx are, there are vocal folds, the superior part of our trachea, and they form the ends of the bones at joints. So in between any articulation point, an articulation point is where two bones meet up. That's where all of our hyaline cartilage is. So when you hear about arthritis, it's wearing down the hyaline cartilage between our bones. So it's bone-on-bone friction, hence the pain, because again, bones are living and they do have a nerve running through them. So that can be painful if you don't have that hyaline cartilage cushioning. Something that's interesting about it is that the entire fetal skeleton is made of hyaline cartilage. If you don't know, the reason babies are so flexible and they can bend in every which direction, when's the last time you saw a 3-month-old with a cast on, even if for some reason they were dropped or fell? It's because their body is made of hyaline cartilage, and as you introduce calcium and protein from both mom through breastfeeding and then other foods, the bones start to harden, and we'll go through that whole process when we get to the skeletal system. Actually, a really sad story that I would have told in class. One of our friends in Jacksonville, Florida, they have a little boy, and they hired a babysitter, and when they got home, their son was screaming, and they didn't know what was wrong. They called the babysitter. She said, "Oh no, it was like a good night, nothing really happened." So they took the baby to the hospital, and the femur ended up in part of the ilium, which is part of the hip bone, the part of the pelvis, ended up cracking. And so immediately when bones, I think their baby is like, or their kid is like 16 months old, that's kind of on the line of when bones really start to solidify. And so CPS took the boy away from them, knowing that something bad had happened, and they start to look into neglect. So not only is their little boy suffering, but now CPS has taken them away to do an investigation. So they call the babysitter again, and she's like, "Oh, well, he might have kind of slipped off of the changing table." And then, long story short, it ends up being that he fell off the changing table completely. Maybe, she wasn't negligent. She probably just walked away to get a diaper or something, but he had completely cracked his hip. So it is possible. Not every kid is the same, but hyaline cartilage ends up turning into bone. The way that you identify it, what I always look at, if you look under a microscope, I think it looks like animal tracks within the rubbery matrix. So this is all going to be matrix. These are the cells. You get some what I think are guitar pick shaped cells, and then the nucleus within it. So I'll circle. They're very diverse types of cells. Some you'll see kind of 2 cells within, and then 2 nuclei within that. Some are guitar pick shaped, and they're all going to fit within what are called chondrocytes, which are these little cell kind of cavities that the actual cell fits in. And so again, this does, remember, you're not getting illustrations on your actual practical, you are getting real slides. So this doesn't really do it justice, but the rubbery matrix is going to have somewhat of a shiny appearance, but I would really look for those animal tracks. And if you think they look like something else, by all means use that. Elastic cartilage, I didn't even put an illustration on here because, it really, they're, here, I'll draw something. What I think they are kind of egg-shaped cells, so they're not perfectly round, and they are going to be embedded within 2 kind of boundaries and other tissue types. The one that you could actually get confused with elastic cartilage, which supports the external ear. You have some elastic cartilage in your nose as well, so it's really flexible cartilage. The one that I actually think you could get confused with is not elastic connective, but rather a hyaline cartilage. So when you're going through your own tissue project, compare those back to back over and over, and do the same as you take other people's practical. Fibrocartilage is another one that you could get confused with either hyaline or elastic cartilage. But the difference is if you flip back, look at the matrix. This is pretty clear right here. You don't see any collagen fibers or anything else in that rubbery matrix, whereas you need to look closely. Right here, there are tons and tons and tons of collagen fibers, all of those strands. So these aren't the cells. These right here are the cells. And the one thing that I always look for in fibrocartilage for the cells are little pin dot nucleus. So you notice I made a really small nucleus versus, again, guitar pick shaped cells or 2 cells together for hyaline cartilage with bigger nuclei. So look at the matrix. Do you see shiny? Oftentimes has a shiny matrix. Do you see strands, which are the collagen? And do you see just a really, really small nucleus? And you notice that the cells are really diverse shaped. So this one versus a smaller one. And so, again, it's just practice looking at them over and over. Really where we see fibrocartilage is in between the vertebrae and then the knee as well. So where we need a lot of cushioning, where you're going to have a lot of force. So you jump down maybe out of a tree or off a house, or you do a jump in cheerleading, you need something highly compressible so that the bones don't bump into each other. You don't want to crack your vertebrae, because then you can start talking about messing up the spinal cord, which is even worse. Bone's not a big deal. When you start dealing with nerves, they're irreparable. You're not going to get neurons back. And so between the knee as well, you need something for cushioning between the femur and the tibia. Dense connective. I would start off waves. When I was looking through your tissue projects or tissue pictures, what I was looking for is the waves. The actual cells are those blue things embedded within the collagen. So cells are called fibroblasts. They actually make the fibers. So all of these cells make the surrounding collagen around it. And the 2 areas that we most often associate with dense connective are going to be tendons and ligaments. Tendons attach muscle to bone and ligaments bone to bone. Ligaments are a little bit more stretchy because if you think of it, our bones need to be flexible as far as movement and moving your bones towards each other if you're going to do a particular motion, versus tendons. You have what are called an origin and insertion point, and those need to be really solidified to the bone. Another thing that I would absolutely know, the third, if you remember back, I said there were 3 different parts of your skin. Really, we'll call it second because we haven't even gotten to the third yet. The second tissue type for your skin, remember the first was stratified squamous, the second, the dermis, the dermal layers underneath the epidermis, is made of dense connective tissue. So this is what your purse, what your leather purse, what your leather shoes are made of. We can't use the epidermis, we can't use stratified squamous because those cells will flake away. We need to use the dermis because these cells are dense connective. When they dye the collagen of a cow, that material isn't going anywhere. It's really hard to damage leather. You might damage the dye on the leather, but it's really hard to damage the actual leather because that dermis is so heavily invaded with collagen, and there's only a few cells within. Because there's so much collagen under a microscope, it ends up, if it's zoomed in enough, which is what I was looking for, it will have kind of a wavy appearance to it. For dense connective, the one that you could get confused with dense is smooth. Smooth muscle. So a completely different category, but I'm just telling you the ones from experience that I see people confuse. Areolar, you really should not get confused with any other tissue type because it looks like cobwebs. They're really pliable. They are all strewn about your entire body. They soak up leaky fluid, so after the exchange between blood, capillaries, and cells that we talked about with diffusion and active transport and cell membrane and all those different things, the areolar tissue will soak up that fluid and deliver that fluid back to the lymphatic system. It is the most widely distributed connective tissue, so it's everywhere throughout the body. It contains all fiber types. So the reason, this is how I would identify it. It looks like a bunch of strings are all throughout the tissue, and then you have these little cells kind of randomly thrown about within, but really the entire tissue is going to be mostly matrix, collagen, elastic, and reticular fibers. If you notice this, it's going to be underneath all the other tissue types of the skin. So as soon as you get deep, underneath is a bad term, deep to the stratified squamous, the dense connective, and then the hypodermis is going to be made of adipose tissue, you will immediately see the areolar tissue. When a pregnant woman swells, when you hear of like swelling in the feet and ankles and skin, it's really not the skin, it's going to be the areolar tissue. So the term edema, if we talk about pulmonary edema, edema is fluid buildup. You can talk about cerebral edema in the brain. Edema is going to be where there's excess fluid in a particular spot. For pregnant women, not as big of a deal. It can cause hypertension, high blood pressure, which can be an issue. But overall, you never want to hear the term edema to any other part of your body, because like in the brain, that fluid can end up causing brain damage to the neurons, just putting pressure on the neurons, or in your lungs, it can lead to infection like pneumonia. The reason I put it with the areolar tissue slide is because areolar tissue can cause acute level, meaning immediate, meaning temporary level fluid buildup in certain parts of our body. Adipose tissue. You'll notice these I always think they look like fluffy clouds. They're going to be white. All you're going to see, you're really not going to see the nucleus because that adipose material, fat, pushes the nucleus over to the side. So you can see the nucleus over to the side. Adipose tissue insulates the body, so it will hold or heat up your internal organs, which generally speaking is a good thing. We want them, they function best at a particular temperature, so even when it's cold outside, it maintains the internal temperature. Protects some organs like the kidneys, like the heart. You have a lot of fat around your heart. You don't want fat inside of the heart, but you do have fat around the heart. And it's our secondary form of energy. So after carbohydrates, you kick into burning fat, which is one of the reasons why you might want to work out in the morning, because if you don't have a huge carb supply, you're going to kick in your fat storage, which is what most people end up wanting to burn off. Remember, this is the third deepest layer, and it makes up the hypodermis. You've heard of a hypodermic needle. You go into this fatty layer because it has a lot of blood supplies, a lot of blood supply in that hypodermis layer, and so you can get whatever you're trying to inject the person in directly into the bloodstream and get it circulating around where you want it to go. The hypodermis is different in males and females. It's also what accounts for the difference between male and female figure. Adipose tissue, I might have said this, I can't remember if it was on the regular PowerPoint or the first one, but adipose tissue is the number one indicator of when you'll get your period, as you know, developing through adolescence. And so if you are a runner, or you don't, you know, you're thinner, you might have an irregular period. It might be harder to get pregnant. I know personally, I know 3 or 4 different girls who, when they went to their doctor, you know, if your period is irregular, that means your ovulation schedule is irregular, which just means it's harder to pinpoint when you could actually get pregnant. And so I always like to make this class relevant, especially because you guys are, you know, all girls and will deal with this at some point in your life. If you run a lot, it can cause, it does not mean you can't get pregnant. It's just, it might prolong the time it takes for you to get pregnant. Because again, they're seen in some countries where obesity in kids is rampant, that girls are getting their periods at like 7, 8, 9 years old consistently, which is really, really young compared to the mean. And it all has to do with adipose tissue, because basically your body is saying at that point, you know, I can get, like, my body could support another living being inside of me. And so, you know, if you're skinnier or have a really low adipose content, until your 7th, 8th, 9th, 6th, you know, it just depends on the person. It can prolong when you get your period, and then later in life, the regularity of your period. And so it does, adipose tissue is the difference between male and female figure, like wider hips. It has solely to do with that, that adipose layer of the hypodermis. Reticular connective, what I would look for visually are the tree branches, and you need to have something zoomed in enough to see those tree branches. Those are reticular fibers, and you'll see these really small cells, again with a pin dot nucleus, so don't get that confused with fibrocartilage. Again, the differences are you're going to see what I think look like these tree branches kind of all throughout the reticular cells. You find reticular tissue in lymph nodes, so all throughout our body. The spleen, which is a really delicate network of cells that dispose of proteins and old cell parts within our body. If you deal with bacteria as well, it's why you can't have a lacerated or ruptured spleen, because it'll drop a lot of the things that are being disposed of into the bloodstream, which can cause sepsis, which is just like system-wide infection. And then the bone marrow. Remember, the bone marrow is different than the skeletal system. So bone marrow is embedded in what are called the epiphyses, the ends of bones. So 2 different tissue types within a bone. We have both bone or osseous material, and we have bone marrow within the actual bone at the ends of bones. Bone marrow in infants is everywhere because they're growing at such a rapid rate, but in adults it ends up transferring to the ends of long bones like your femur and your humerus, and to the pelvis, hips. Blood, I'm not even going to talk visually about what it is. Nobody in here should miss this question. Really small red, it's always going to be red. Donut-shaped cells. The matrix is made, instead of reticular fibers or collagen fibers, it's going to be made of proteins. Proteins make up the plasma, like the antibodies that we look for in the ELISA lab are part of the blood plasma. You know what blood does already from our first chapter. It's going to transport materials to our cells. Iron is really important. I've heard a few people who are iron deficient already this year. Iron is going to form the central component of hemoglobin, allowing for oxygen attachment to the actual red blood cell to be carried, to the actual other cells of the body to diffuse in and carbon dioxide to diffuse out. The reason carbon monoxide is so toxic to us is it compromises the oxygen carrying ability of our red blood cells to the rest of the body. So if you don't have oxygen, you're in trouble. Okay, so now we are on to muscle. We just concluded connective tissue, so this is a logical stopping place. For those people that want to leave off and come back, this is a great spot. Muscle tissue, there are going to be 3 types, so not as many as connective tissue. These two are the ones that you could get confused, and I'll point out why and how you differentiate between them. So skeletal muscle, do not get confused like when we say skeletal muscle versus the skeleton. The skeleton, made up of bones, everyone knows that, but skeletal muscle are like our biceps, our triceps, our quad, our hamstring, our calf muscle that attaches to the bones. The reason we call it skeletal muscle, again, because of tendons, bones and muscles work hand in hand together, which is why we study them back to back. Cardiac muscle is only in the heart, and then smooth muscle in our hollow organs, like our bladder. Remember, our bladder is an organ. We've already gone through transitional epithelium, remember, with the fluffier cells that have the ability to expand and contract. But the actual muscle that is going to move things out of our bladder will be smooth muscle, and the stomach as well. The thing that combines all of these together, all 3 of these tissue types, is movement. Remember, movement, skeletal muscle is going to help us move, and it's voluntary. The other 2 are involuntary, but they still are going to, the cardiac muscle is going to pump, with the pacemaker, and then smooth muscle is going to purge things out, move things from one location to another. So visually, skeletal and cardiac look similar. Smooth looks nothing like them, but they all, the common thread for all of them is that they move things or they move themselves. Skeletal muscle. Look for the bands on a snake. That's the one thing I made sure in everyone's slides that they sent me. You need to be able to see those little tick marks in a clear pattern throughout these entire cells. So this right here is one cell, and then they have all these proteins called actin and myosin within the cells. Actin and myosin are the proteins that are going to latch onto each other when you flex. So it's a really complex concept. We'll spend a few days on it, look at animations. It's a really long process, in depth, involves calcium, and involves multiple proteins outside of actin and myosin. And so skeletal muscle, the key identifying characteristics are that skeletal muscle cells have striations, those snake bands. I always think it looks like snake skin. Cells attached to connective tissue is just saying that skeletal muscle is always going to attach, to bones or use like tendons to attach to bones. Cells are striated. That's what those bands are called. And then they often have more than one nucleus. If you're in here right now, I'd ask you why, or it might be a poll everywhere question, why you think they have more than one nucleus. It's because, remember, that it is the only tissue type in the human body that is voluntary. Multiple nuclei help coordinate impulses from the brain to tell the muscle cells what to do. Muscle fibers and muscle cells are the exact same thing. And so visually, I told you that cardiac tissue looks very similar. Notice that they have striations that look exactly the same. Cardiac tissue is involuntary. You might be able to tell that they're, instead of multiple nuclei, because of the voluntary nature of skeletal muscle, that there's only one nucleus per cell. But what I want you to look for are these intercalated discs. Cardiac cells are smaller, they're more abbreviated. Then skeletal muscle cells. Skeletal muscle cells can be up to 2 feet long, which is a weird thing to think about, that a cell could be 2 feet long. But think about some of like how long our quad or our hamstring muscles are. So some of those cells are really long versus cardiac cells, because of the depolarization or action potential, basically meaning the heart beating, we need to have more abbreviated cells. And because of that, look for those intercalated discs that darkened. They'll be stained usually fairly well on a slide. The intercalated discs are going to break up the cardiac cells. Smooth muscle. Remember that I said you might get this confused with dense. So a completely different category of tissue, you might visually get confused with smooth muscle. What I look for is that, yes, there's one nucleus, but they're going to be really long, spindly shaped cells. So not 2 feet cells like skeletal muscle. They do not have striations. Notice visually they look nothing like skeletal or cardiac muscle. Again, you might get it confused with dense. Notice how long these cells are. And the other thing that I always look for within this, really elongated oval nuclei. Versus everything else, remember, had like a pin dot nucleus or maybe a guitar pick shaped cell and a larger nucleus. Dense connective, remember, it has the waves and the cells kind of within it, but the cells are not part of the nuclei. The cells are not part of a larger cell. While you might think that this is the cell, it's not. This is the nucleus, part of a larger cell. So they're spindle, elongated, almost like a tadpole looking type cell. Another thing that you can see for cardiac tissue is that there might be spaces between them, versus skeletal muscle, you're really not going to see that. Okay, and our last tissue category and type put together, because there's only one tissue type in neural tissue, and what you want to look for visually are the axons and dendrites. So whether it be one neuron or multiple neurons, you want to look for a cell body and all of these different extensions coming off of it, which is the way that neurons communicate. So they send impulses to other parts of the body, to every system of the body. 2 terms that you really need to define, because we're going to refer to them throughout the year: irritability versus conductivity. Irritability is the ability to receive an impulse, and sometimes that is compromised. That might have to do with the dendrites of a neuron, which are like the catcher's mitts of all incoming impulses. And then the conductivity is the ability to send impulses. So I just put marks there indicating that instead of ability to receive impulses, ability to send impulses, and instead it would be the axons that might be compromised. Sometimes neurons can't conduct an impulse, send an impulse. Sometimes they can't receive an impulse. And so we'll look at that in the nervous system chapter, but just pointing out that all of those extensions do have a direct proportionality to what they do. So this does not have to do with one particular tissue category or type, but this is tissue repair in general. So it's going to be different per type, but I'm talking about tissues, like what happens if you injure them. Many types of cells, like our skin, can regenerate, simply regenerate. They just, if they're damaged, you'll get new ones very quickly. Some you're going to, if you damage, so this might be stratified squamous. Fibrosis, if you cut down to the dense connective tissue in your skin, you might get scar tissue. Fibrosis is the process of forming scar tissue. How things repair are dependent on 2 things: severity, like how badly you injured it, how badly you tore something or cut it, or a heart attack. You know, you didn't physically or mechanically puncture the heart. It's just that some of the heart cells were being overworked for one reason or another, and now you might be left with scar tissue. So the type of tissue definitely matters as just as much as the severity. I would definitely know the events in tissue repair, like what actually happens when tissue types repair themselves. Number one, first and foremost, blood is always the most important property in how well, or most important factor rather, in how a tissue repairs itself. So remember, vascularity, tendons, ligaments, dense connective, does not have that great of a blood supply, and so it's not going to repair itself that well, versus osseous or bone tissue really does have a good blood supply. Skeletal muscle, if you tear your hamstring, you're going to be out for a long time. Not that great of a blood supply. So first and foremost, capillaries become very permeable, just meaning the pores are going to open up, which ultimately means that we're going to have more blood flowing to that particular region to start repairing it. Second, introduce clotting proteins so that we don't bleed out. Bleeding internally, bleeding externally, either way, we don't want to lose our blood supply, because the less blood we have, the less oxygen and nutrients we have, the less oxygen and nutrients we have, the longer it's going to take to repair. So those clotting proteins are going to wall off the injured area. In addition to more blood, we also want to limit bacteria from getting in and causing infection. The reason so many people used to die in surgery is not necessarily because of technique, it was because of sanitation. We didn't have the knowledge or the anti-bacterial, antiseptic, preventative measures to make sure that an area is cleaned up. It's why they'll put, the iodine on you when they clean an area before surgery, because that has an antiseptic quality. Formulation of granulation tissue. Granulation tissue is that pink tissue. So if you've ever peeled a scab, you know that kind of pink, fresh material, it's not completely reformed, but it's kind of the walled off heavy blood supply, which is why it's pink. But that granulation tissue is kind of the first layer of whatever tissue type we're talking about before the final repair. And then finally, regeneration of surface epithelium over the scar. So that granulation tissue can turn into fibrosis with some tissue types, so it can scar. Not every tissue, something that you did to your tissue is going to cause scar tissue, but again, depending on how deep you cut something and the tissue type, sometimes it will cause scar tissue. So granulation tissue is the pink transitioning into the scar tissue, and then finally the surface epithelium over the scar, which is why things like vitamin E, which will help skin regenerate. Even if you have a scar, it will become less noticeable over time, just because surface epithelium will form over the top. Tissues that regenerate really easily, so almost all epithelial tissues regenerate really easily. Fibrous connective and bone, 4 to 6 weeks for most bone breaks. Skeletal muscle is poorly, so it takes a long time for skeletal muscle, if you tear a muscle fiber, to reform. And then scar tissue, cardiac muscle, you will always have a scar if you damage any of those cells. And then neural tissue, it's somewhat of a myth that you'll never have more neurons after birth, but it's few and far between. We can regenerate what are called neuroglia, all the cells that hold the neurons together, which is what a brain tumor is. Your neurons are not the ones that mitotically divide to form a tumor. It's all of the other cells that clean up the brain that form a tumor. So the nerve and spinal cord are cells that you're really not going to regenerate at all. It's just going to be, if you sever your spinal cord, that's A, why they try and freeze the cells so that they can get you in and treat you, but B, if it is truly severed, it's irreparable. You're not backtracking. Those cells are damaged for life. And then starting with every system, or ending every system this year, and kind of starting the transition to our first real system, which is INTEG. How tissues change with age. So everything in here is going to be a combination of genetics and environment. Some people have more melanin in their skin, so guess what? Their likelihood that they get skin cancer is much less than a fair-skinned person. So that obviously affects people differently as far as their tissue. Melanoma is going to affect our epithelium. But that's not to say that one person, so two people with the same melanin or skin coloration, one is out in the sun and never puts sunscreen on, the other one puts sunscreen on religiously. Well, it's silly to think, like anything else in life, that environment does not impact our tissues based on what we do. Epithelium thins with age, so we lose the elastic fibers and the collagen, and so skin starts to sag. Exocrine glands are less active, so we have less oils to the surface of our skin, which is why in puberty you start to see acne and zits because of the sebaceous glands become more active, and it's released onto our skin, which you end up getting a small bacterial infection on your skin. Those just decrease with age. So the flip side of that is youthful skin is kind of glowing, if you've ever heard that term, and gives the appearance of youth, versus people that are older lack kind of that shiny, youthful appearance. Hormones change metabolism and reproduction, so testosterone and estrogen production, change with age, like with, menopause. Bones become more porous and weaken, so osteoporosis, the incidence increases with age. Circulatory system is not as efficient because you clog your pipes up over time. And then muscles begin to atrophy, so they break down over time just because you don't use them as much. And atrophying, like if you've ever had a cast, you can see your muscles becoming kind of mushy over time. Okay, so that's it for histology.